You were on the email. Do you have the order of presentation?
What's your stuff here?
Oh. No, he's not. Oh, the microphone is not working.
Is it on? Test 1, 2. Is the display on? Make sure the blue light is on the dongle. Should be a blue light blinking. Press the on button. It'll start blinking blue. This is power. It has to stay plugged in. It is.
You want this off?
We're starting with that.
We're starting with,
You tell me.
Is it YouTube?
Yeah, it's recording on
And so, do you want the screen like this, or do you want the accent?
That's fine. Yeah, we don't want to move it.
Oh, I mean on the screen, like.
That's too late. Thank you. At least we'll do less
Should we start first Zoom or
Zoom. How do you make it bigger?
that?
Or do you want it like that?
It's full screen. Yeah, I can full screen. I'm already full screen.
Okay.
might have to go vocal hold.
Hi everyone, we will go ahead and get started. Thank you everyone so much for attending today's event at the International Museum of Surgical Science. For those of you that have never been here before, we are a museum dedicated to the, I apologize, the microphone is not working today, so can everyone hear me? Okay, good. So the International Museum of Surgical Science, for those of you that have never been here before, we are a museum dedicated to the history and advancements and art of surgery and related fields in medicine. We are very excited to have just opened this new exhibition called Health in Space, Daring to Explore. The Health in Space, Daring to Explore exhibition was developed by the Canada Aviation and Space Museum, one of 3 museums under Ingenuum, Canada's Museums of Science and Innovation, in collaboration with the Canadian Space Agency. You'll have a chance to look at this exhibit upstairs on the 4th floor after today's presentation. We also, in companion with this traveling exhibition, developed the New Technologies in Space Medicine exhibit. This exhibit was developed in partnership with NASA, Virtual Incision, Axiom Space, the Beckman Institute for Advanced Science and Technology, the Translational Research Institute for Space Health, and the Japanese Cultural Center. I would also like to thank our exhibition sponsor. The leading sponsor is the Museums of Quinte. The Museums of Quinte are coming to a site on the Bay of Quinte in southern Ontario between Toronto and Montreal. The site will consist of a campus of 6 distinct museums plus a large botanic garden. The technology used in gaming and practical education will provide dynamic learning experiences about medicine, space, science, and much more. And the representatives of Museums of Quinte are here today that you can meet them in the library right behind you. And I would like to introduce to say a few welcoming remarks. The Executive Director of the International College of Surgeons, Max Downham. Max Downham is the International Executive Director of the International College of Surgeons, or ICS, an organization of 8,000 surgeons in more than 100 countries that serve as the parent body of the International Museum of Surgical Science. He holds a BS CHE degree from Purdue University and an MBA from the Wharton School of the University of Pennsylvania. Mr. Downham served in the United States Navy for 10 years, including serving on a small ocean-going combatant, United States Naval Postgraduate School as an officer instructor. His career in industry includes experience at the medical instrumentation firm Nuclear Chicago and as senior vice president of the pharmaceutical firm GD Searle & Company, where he was a lead member of the NutraSuite commercialization team. He is responsible for the overall management of the ICS, including membership, surgical team coordination, selection of young surgeons for scholarship awards, and publication of the college's surgical journal and management of the International Museum of Surgical Science. Please welcome Mr. Downham.
Well, thank you very, very much, Michelle. The message I want to very simply and brief to deliver to all of you is that number one, we're humbled and appreciate greatly your interest in being here, and we hope that you find it productive and interesting, and you learn something new. And I want to greet Dr. Farritor, who was here just a couple of evenings ago, and Dr. Bianco, I think I've said that right, and also Ms. Wagner. Where are you?
She's here virtually tonight.
Oh, okay, she's not here, so I greet you, Ms. Wagner. And You are in good hands because Michelle Rinard is who put this together. She's been with the college for 8 years. She is absolutely superb. And, kudos to you, Michelle. The museum has been in existence since 1954, about 70 years. We are just proud as we can be to host this exhibit. And so, Michelle, I thank you very, very much for allowing me to speak here briefly.
So I'm happy to introduce our first speaker, Rachael Wagner. She's from the University of Nebraska-Lincoln and is a PhD candidate. Rachael, can you hear us okay?
It's pretty muffled, but I can mostly understand. Can you guys hear me all right?
We'll let Steve figure
Try
out.
that. Go ahead and test it.
In that case, actually, I can get started.
So I'll
Are you
introduce
hearing me?
you, Rachael, I just want to
But thanks for letting me join. I'm currently in Japan right now. I have a summer retreat abroad experience that I'm really excited to be a part of, but unfortunately it means I can't be with you all today. But I'm glad that I'm still sharing experiences and hopefully it's still stable. Hopefully show you some interesting pictures and video of our experience with sending space to the International Space Station.
Rachael, can you hear me? Rachael can't hear me.
Yeah.
She can now. Can you hear me, Rachael?
Mm-hmm.
I just wanted to give the audience a little bit of your background. So Rachael Wagner is a biomedical engineering PhD student at the University of Nebraska-Lincoln. Her research interests include space technology and surgical robotics. She graduated with a bachelor's from UNL in 2018 and worked at Virtual Incision in Lincoln before pursuing a graduate degree. So please help me to welcome Rachael Wagner.
Thank you. I can see you guys on the laptop in front, so I feel like I'm there a little. I still am not able to share slides, so let me know. You're good. Here we go. That looking?
Yeah.
Yes.
Well, thanks for my wonderful introduction. Like I said, I'm really able that I'm glad that I can participate with you all. Even though on the other side of the world, and it is quite late at night right now. But again, my excitement about the project is pretty high, and we're eagerly awaiting our payload return. I'm going to tell you guys a little bit about what this journey has been like for me. So we started off with this concept that we pitched to NASA in the grant proposal, where we wanted to put the space mirror version of the mirror surgical robot in an express track locker, which is their standard experiment capsule, on the International Space Station, and try to see what it's like to do simulated critical tasks in microgravity, and considering the latency it takes to get from space to ground from the ISS. So we proposed this idea to NASA, and thankfully they were supportive and funded this grant. And so in order to get to our final version of this payload, we built 3 prototypes, as I like to call it. The first one that you see on the left is pretty bare bones, not so much going on, but you can see a lot of similarities still carry over all the way to our or third iteration. We oriented the robot diagonally in the locker. We experimented with several different types of surgical tasks that we would want to potentially do in space. And then you can also see that the cabling is exiting through the front of our box there. And that was something that carried through throughout this entire process. Our second prototype was fully functional, meaning that all the computer and hardware and electrical equipment was very, very similar to our final device. And with this, we were able to kind of perfect a lot of our code and computer programming that we needed for the ISS project. And then lastly, on the far right, you can see our ground unit, which is identical to the payload that we sent to space, except for instead of taking to space, this one was used for testing. And this testing was needed to prove that the payload would be ready to send to space and that it would be safe for the astronauts to use. So in order to accomplish that goal, NASA provided a lot of help. We met with them weekly, and they provided feedback with engineers from all these different teams. So payload interfaces and operations. We had lots of software and safety integration meetings, and then we also had an input from manufacturers engineer that helped us design what the user interface for the astronauts would look like. So this is the control panel that we ended up designing that one of the astronauts ended up using on the ISS. And there's some things that you might not think about when you're designing something to go to space. And one of those that I did not think about was labeling. And so it was definitely an interesting journey to talk with our manufacturing engineers and learn about all the different things you have to think about when you're designing something to be as easy as possible to use for the astronauts in space. We also had to include labeling on the inside of the payload, which you guys might happen to see in the exhibit. One of the things that NASA was pretty concerned about was the scissors on the robot device. They are bullet-tip safety scissors. We wanted to make sure that there was no possible way that we would accidentally give an astronaut a cut, as I like to joke. So you can see some of the labeling that we need to do there to make sure that everything went smoothly along with it. Once we had finalized our design, including our labeling design, we moved on to the testing phase of this project. And there were several phases of tests that we needed to do in order to prove to NASA that we had met the requirements for both safety, but also a lot of the specific tests I'm going to talk to you about right now. The first one was power quality testing. And for this, we actually had to travel to Huntsville, Alabama to visit Marshall Space Flight Center there. They have the only power supply on Earth that is identical to what is on the ISS. So in order to prove that our payload was compatible with the power supply in space, we had to go test the robot and the payload there in person. And thankfully, the engineers there were very supportive and helpful, and we were able to pass this test successfully during our trip. Another test that we had to do was electrical compatibility testing. So anything that runs on electricity emits electromagnetic waves in the non-visible spectrum for the most part. And so you want to make sure that your emissions do not interfere with the other ISS systems. It's very important that everything continues to run smoothly on the ISS, and we did not want to be the payload that messed that up. So in order to do that, we took the payload to NCAA lab in Nebraska, and we were able to test in the Bianco chamber that they have there in order to see what levels of emissions our payload put out. And thankfully, we were able to also eventually pass this test, making sure that we'd be compatible with ISS. And this was a very interesting experience for me, as I'm not an electrical engineer by training, so I learned a lot about what those guys do. Crazy stuff. Then we had to do vibration testing. And so, as you can imagine, going to space is pretty rigorous. You have to fly on a rocket, and and that rocket ride would get pretty bumpy. So in order to make sure that our payload would survive the launch, we simulated a launch condition where the payload was vibrated on all three sides to prove that it could survive the rocket launch. And thankfully everything did. It did great. NASA was in particular concerned that the scissors wouldn't open during the launch, and so that was one particular thing that we were paying attention to during this test. Another thing we had to do was acoustics. So we took the payload into a very quiet chamber and we measured the sound emitted while in normal operation. And in order to run the payload continuously, we needed to prove to NASA that the sound was below a certain decibel level for protecting the astronauts' hearing. And then also, I think, when you're on the ISS, there's no outside you can go to escape the high-pitched buzz sound that could be created. So we wanted to make sure we were quiet and weren't creating any annoying beats or anything. So that was kind of the purpose of this test, and you can see that kind of sounds are set up according to their guidelines to prove that the payload was good to go. And then once we satisfied all of our requirements, we actually shipped the payload off to NASA and it waited a while until we caught a ride on the NG-20 launch earlier this year in January. This was a special launch because it was the first time a Northrop Grumman Cygnus spacecraft had been launched on SpaceX Falcon 9 rocket. And so it was kind of cool to be a part of that piece of history. The payload docked with the ISS on, I believe it was February 2nd. Of this year, and then we waited until we got unpacked and we were ready to go for our experiments. So this is a picture of the installation process. That's actually astronaut Laurel O'Hara installing the payload on board the ISS into an express rack, where in order to get set up and ready to go, all we needed to do was get plugged in and then connected to internet. And we would be able to talk to the field and watch what was going on from Earth. So definitely this was an exciting moment for me in order to be able to talk with the NASA mission control and to go through some training in order to learn how to use the radio speak that they have and the special software that they use to talk to astronauts. And then you can also see that we had the timeline of what all the astronauts were doing pulled up as well. So it was really cool to see live when they were ready to start putting our payload in. Then we began our deployment portion of the experiment, and so we had the robot cut some of our simulated tissue or the fancy rubber band using the onboard computer and the payload to compare some data that we would get on Earth with computer control and then also in space. And so thankfully that has been super smooth. You can see everyone smiling in the picture. We're watching the robot do its thing. But after the autonomous experiment, it was turning toward the exciting part, which is the remote control section. And so this is a picture of us participating in that experiment. And this is where we had a surgeon control the surgical robot from Earth. So you can see one of our surgeons here at the surgeon console, controlling the robot and cutting rubber bands while it is up in space. And there was some latency that we had to deal with conducting this experiment, so that the surgeons had to be really on their game to make sure that that didn't phase them. But thankfully, everyone was able to successfully dissect their rubber bands and complete all the surgical tasks that we had both, which was super awesome. We got lots of good data. And we also got to let me have a try, which I was totally not expecting. But I was able to dissect one rubber band without breaking the robot, even though I'm not a surgeon. And that was really special and kind of a full circle moment for me. At the end, Laurel O'Hara hooked us up again and uninstalled our payload and packed it up to get returned to us. And you can see we got historical photos of her in the robot, which was a pretty cool moment for so now we're just waiting for the paper to come back, and I'm really excited to take a look at the data that we'll get back, so we can kind of compare the data that we collected on Earth with the data we collected in space, see what we can learn there. And then also, I'm really interested in the user experience of the surgeons conducting the experiment and what they see like for them, and if there's any tips that they have to share about what it would look like to do more post-surgery experiments in crazy far off places in the future. So thank you everyone for listening to my short talk here, and I guess we'll open the floor up for any questions if we have any. I don't know if we're good on time now, but thank you.
Does anyone have any questions for Rachel? We'll just check the YouTube.
I have a question.
Oh, sure.
Was there a delay when the surgeon from Earth was trying to cut something in space? Because you could see
I
it, but
didn't
then,
quite catch that.
I'll repeat the question. What did you say?
was there a delay when the surgeon on Earth was trying to cut something up there? Because light is faster than we can see.
Was there a delay in cutting up in space?
Yes, there was a delay. So we were seeing about 650 milliseconds to 800 milliseconds of delay during this experiment. So that's like 6/10 to 8/10 of a second, which is pretty significant. I think most surgeons probably wouldn't prefer them to be that latency. But like I said, they're pros, so we were able to kind of overcome that hurdle and get the job done.
Yeah, do you have any expectations or hypotheses about how surgery in microgravity would differ from surgery here on Earth? Or what would you investigate? Yeah. How do you expect surgery in microgravity would differ from surgery here on Earth? Are there expectations or hypotheses that you're trying to test?
How do you expect that surgery in microgravity would be different from surgery here on Earth?
So they've looked into this a little bit, and for a human doing surgery in microgravity, it's a bit challenging because you have to accommodate for the fact that gravity, which you normally rely on during surgery, is not there. And so it requires extensive training, is my understanding, to kind of compensate for that. So one of the things that we were looking at in this technology demonstration is, the robot theoretically doesn't care about gravity. It should be able to kind of do its thing, whether or not there's gravity there or not. So I think looking deeper into the data might help us understand if that truly was the case during this experiment. But we're going to see what we find out, and I think we'll get some good direction that would be worth further investigation.
Any other questions?
How does post-operative or just wound care in general function in space, like, as opposed to on Earth? Did you guys account for kind of like the post-operative aspect of the process?
How does post-operative care act in space and wound care healing?
I didn't quite get to that part, I'm sorry.
How do you account for post-operative care in space after the surgery and wound care?
Yeah, how wound care works.
Yeah, that's a good question. I think NASA is probably doing a lot of work in that area. If we ever were to do surgery in space, and they might already have some protocols in place for if emergencies do happen at the moment. But I think we're more focused on using the robot for surgery in space, and I'm not an expert in post-operative care. So ask NASA is maybe not a great answer. So you do know a lot, you know what they're doing.
Have you some experience for the animal surgery in the space?
Have you done experiments on animal surgeries in space? Is that?
There have been animal surgeries in space, very limited, and there's also been animal surgeries in zero-G flight, but none of them, to my knowledge, have been robotic.
Okay. Any other questions? Okay, great. Thank you so much, Rachel. So we'll
Thank
move
you.
on to our next speaker, and Dr. Bianco. To introduce to you our next speaker, Shane Farritor, PhD and MS from Virtual Incision. Dr. Shane Farritor holds a doctorate and master's degree in mechanical engineering from MIT and is currently a faculty member at the University of Nebraska-Lincoln. Prior to his work at the university, Shane studied at the Kennedy Space Center, Goddard Space Flight Center, and the Jet Propulsion Laboratory. Shane holds over 170 patents and has published over 140 peer-reviewed articles in the field of robotics. Please help me to welcome Dr. Farritor. Steve, do we have the clicker?
It should be up there.
Great, really happy to be here. So Dr. Bianco and myself and Rachael are all working together on the same project. We're going to tell you about the same stuff here. We all bring different perspectives. Rachel's fantastic. She's about to get her PhD. She actually accepted a teaching position at the University of Nebraska as a professor. She's got to finish up that PhD, so we're all trying to push her along. So it was great that she could join us today. The work that Dr. Bianco and I will tell you about, that's actually what she did. We're just going to take credit for it. Academia works. So, well, first of all, let me just show you this. This is the robot we're all talking about. Here it is, right there. This is our surgical robot. It's called Mira. So I am a faculty. I'm a professor of engineering at the University of Nebraska, but I'm also co-founder of a company called Virtual Incision that's developing this for clinical use. So the first thing that's incredibly different about this than all other robotic systems is that it's very small. Robotic surgery systems out there are very large. They can be up to 9 feet tall and they weigh about 2,000 pounds. So it's a much, much different approach than this. What's similar with them all is that they all have a console. So in some ways, the surgeon is remote from the patient. They use this to control the device. The robot really doesn't do surgery. The robot does exactly what the surgeon tells it to do. And the surgeon will sit across the room at a console and control the robot somewhat remotely. What we've done here in this experiment is we've made it very remote by putting the robot on the International Space Station. So that's just the basics. The last thing I'll point out is that there's a camera, laparoscopic camera. The device is made like you and I are made. You got a right hand and you got a left hand. You have two arms, and then you have this camera like your head that looks around left, right, and down. And that's like you shrunk the surgeon down and put them inside the patient. So when they do what's called laparoscopic surgery, they actually inflate you. And it's like putting a salad bowl on your belly. It lifts your abdominal wall up. And there's kind of that much space in there. We put the robot inside your body. So everything below my hands goes inside the body. And then the surgeon can do surgery. Does that basic idea make sense? Any questions about that? We're going to have a small group to ask questions as we go. What's exciting? Well, what's very exciting is we just February 23rd received FDA marketing authorization. So we're just now beginning to bring our product to market, and we hope to be doing surgeries in a few hospitals before the end of this year. So it's a very exciting time for us. You'll notice some of Rachael's dates around February too. We had a very busy month of February with our space station flight and FDA approval. I always have to point out that the application was 35,000 pages. It took a while to put the application together. A lot of effort there. And we did a 30-patient clinical trial as part of that too. Quite well. The
The robot is waterproof. This doesn't mean much to some folks, but almost everything in the operating room is covered with drapes. And so there's a plastic barrier between sterile environment of surgery and other objects. Not with our device. It's sterilized and used just like this. So you can wash it under a sink after it's used, and actually the robot is designed to be used 15 times, 5 times. So anyway, we made a funny video just to show that it's sterilizing. The fish are very easy to catch, we didn't harm any fish in the video. Our robot's really strong, some people ask about the small size. It's still very, very strong. You need some strength to close hernia go to move colon around, and things like that inside the body. So we took a version of this as with my class on small robots for surgery. And I'm interested in our work because both the Army and NASA want to do surgery in crazy places. Almost all soldiers die in the first half hour after injury or the golden hour. Sometimes they stretch it too, but you need to get surgical care to soldiers very, very quickly. And if you can do that remotely with a surgeon at a remote site, I think there's potential there. So NASA came to us and asked if we actually gave us a grant to fly in the International Space Station, sort of as a capstone of all of our research. So Rachael talked a little bit about pre-launch testing, and she showed this experiment locker. This is about the size of a microwave. It's kind of this big-ish. It's upstairs. Everybody needs to go up and see it. Space Mira and so this robot and this box are upstairs. Everybody needs to go check those out. But they connected power and Ethernet, and then they really just flipped our switch on. And that's really all we asked them to prove. And there was a question earlier. This was really just a technology demonstration. It's the first step to show what's possible. If you're thinking about surgery in space, things have gone very, very poorly. You're in a tough spot. That's kind of down the road further. But it's something that's going to have to be thought of because, return from low Earth orbit can be reasonably quick, but not from Mars and not from the moon and not from asteroids. So as NASA plans to go further out, this kind of thing will be more and more important. So Rachael on the right, some other students there. Rachael kind of described all the testing that was performed. Launch is fun. It's just my policy that if you have a picture of a rocket launching your robot to space, you should play that video every time. So I will do this every presentation. Just because. But we got to go down and see the launch. And that first stage of Falcon 9 coming back is as spectacular as you see it. This one came back to the landing site to land. Sometimes they land out on the drone ships. It's pretty spectacular. As Rachael mentioned, we were on the Cygnus Northrop Grumman cargo ship. So it takes a couple days to get to the space station, but here it is arriving at the space station. And then the device was installed. So there's our microwave-sized box. And again, that's astronaut Laurel, expert on flight. So Canadarm, she's the Canadarm expert there. But she's sliding our box into this express rack. Kind of a holdover from the space shuttle days. It's just kind of a standard box. So she installed that for us. So you can see the yellow and red connectors where she will install the power and video. Then we had her check 2 connections. So she took her flashlight and looked around to make sure everything was connected. And let me just say, I shouldn't act surprised. Everything worked perfectly on this flight. Everything was fantastic. Nothing was broken. And I don't really, again, I shouldn't act surprised. Right? As soon as she did that, she turned it on. And the robot, as Rachael mentioned, went through a pre-programmed path. So we'd actually cut some rubber bands on Earth, we recorded that path, and we redid that on the space station. So the video on your right is actually happening on the space station on, I don't know, February 6th or something like that this year, not too long ago. But you can see, we call it simulated surgical tissue, but they're rubber bands, right? And an act of surgery that's very common is you grab tissue, you retract it to provide tension, and then you perform a dissection of that tissue. And so that's what's happening here. You can also see how there are cameras moving around so that you have a nice view of your surgical target at all times. And we have rubber bands positioned kind of in a large area. So first thing, before we did anything else, we just had to cut its own tissues. At least we would get this video. You saw some trouble setting up the Zoom this morning, right? It's always hard to make connections like that. So even if you weren't able to make a connection, you wanted some sort of activity. Does that make sense? This was stage 1 of our experiment. Stage 2 was teleoperation, where we would control it from the ground. And you saw some of these images before, but we made our own little mission control in our facility in Lincoln. First of all, there's a row of engineers. You can see Rachael here, and she's speaking with the astronauts and Capcom, the Capsule Communications. In the back row is our group of surgeons. Bianco here, waiting his turn. Jobst, who's actually controlling the device. So you can see this. That image is coming from the space station, and he's using the console to control the motion of the robot to actually perform those surgeries. You asked about the latency earlier. Yes, there's plenty of latency. The space station is either 250 miles right above us, but it orbits the Earth, of course. So it orbits in about 90 minutes, and we were operating for about 2 hours. So it was either straight overhead, or it could be about 8,000 miles away on the other side of the Earth, of course. So we actually communicated with Marshall Space Flight Center. The signals then went to White Sands, New Mexico, then up to what are called teacher satellites, which are communication satellites that are dedicated by NASA. And that leads to all this this switching and this handing off with a lot of extra latency. And then in the back row are the 6 surgeons. We had 6 surgeons who participated in this experiment. These are just general images from the space station up here. Again, this is our image from our robot and our camera. And then this is the loss of signal. There's an S-band and a KU band antenna. We had to be mindful of the loss of signal, that they're not always in communication as they orbit. Here we go. This is our 6 astrosurgeons. And you're going to hear from Dr. Bianco here in a moment. He's from here in Chicago, Los Angeles, 2 surgeons from Nebraska, Houston, and New Jersey. So we wanted a diversity of surgeons that would try the experiment and see if they could all do it. And they were all very, very successful. The latency is not ideal, but it turns out the surgeons just were a little bit slower. And actually, surgeons who have done the same task on the space station with delay or on Earth with the normal system, it takes about twice as long to complete the same task with the latency, but they're equally successful. So we have some preliminary experiments on that, but again, we're waiting for our payload to come back. Here's just a video, Rachael talking on the Capcom, a surgeon controlling the device. This is a surgeon cutting from Earth. Those are the hand controllers that are used to control the motion of the robot. You can see the camera moving there. I think that was Dr. Bianco there. Rachael and I got to sit down and do a little bit. And then there's our experiment from the left there. We had a nice group who made a big shindig out of the whole thing. Dr. Fong was very excited. And then our system has been uninstalled. Astronaut Laura O'Hara, again, Rachael showed this image. It came down, it's down on Earth. Astronaut O'Hara is also back on Earth. But our experiment is also on Earth. We're waiting for them to ship it to Nebraska. We haven't seen it yet. But I point this out, and Dr. Bianco will talk a little bit more about this stuff in a second, but we just recently, April 30th, maybe May 1st, somewhere in there, had an experiment where we did surgery. We had 4 surgeons in Chicago and 4 surgeons in Lincoln, Nebraska. And we had 2 animals on each side to do practice surgeries with. And we did a total of 8 procedures that day. 4 from Chicago to Lincoln, and then 4 from Lincoln back to Chicago. And this is really where we want to go. Now, on the space station, the latency was again around 600 or 800 milliseconds, pretty significant. But here, between Chicago and Lincoln, it was 15 milliseconds. So really not noticeable. And again, Dr. Bianco can speak to that more directly. But we did several different types of surgeries, from gallbladders to colons to hysterectomy. We did a couple of nephrectomies, removing some kidneys, and it was really quite successful. And we think this has, again, potential for remote locations. Nebraska is a rural state. There's small hospitals in small towns with general surgeons, but maybe they don't do nephrectomies and maybe they don't do colectomies. very frequently, just because that's not their patient population. But if you can have a surgeon, an expert, dial in from a remote location and help with a surgery like that, keep that patient local, let them stay home, that could be a big win. And then we'll eventually go back to our military roots and start looking at that problem again. But we think there's a lot of potential. This is all possible because this is small. This is launchable to the space station. This is deployable into small communities and forward environments. Big 8,000 pound, 2,000 pound robots that are 9 feet tall are much more difficult to do that. Actually, the big robot company just introduced a new robot. They bring a semi around to show people the robot. You can hop in the back of the 18-wheeler and see the device. So, the venture is huge. Now, I've kind of talked from the engineering perspective. We're going to have Dr. Bianco now talk about his experience surgical. This is the Museum of Surgical Science with a display on space medicine. So the overlap of those two is us, space surgery. Yeah.
You mentioned the device was to be used 15 times.
Yes.
What happens after that? Is it disposed of or sanitized?
So our FDA approval says it's disposed of. However, we've been doing the testing, and we think we can do up to 4 cycles of 15 times. So you bring it back, basically you throw away all the plastic, all the electronics, but the motors and gears on the inside of this, we've shown can be reused. And so you rebuild a new robot and send it out as new. And that upsets the apple cart of pricing all of a sudden. We think we're cost competitive with other approaches with this, but when this goes from 15 uses to 60 uses, it really changes things a lot. My emphasis with this robot is not that it's small, but it's simple, easy to use. It makes sense to everybody. Everybody kind of gets how it works. And it's easy to set up, easy to move from room to room. Simple, simple, simple is really what we push for. And with that, we think will come, eventually come cost advantages. Yeah?
Excuse me, how big is the port to serve?
So this is about 35 or 40 millimeters, and our clearance is actually for colorectal surgery. And I would only use this robot for colorectal surgery. Your colon is a big organ that has to be removed. You get colon cancer and then you have colectomy. And so they need a larger incision for that anyway. So the total incision size is less for this robot. During our trial, they would make an incision for this robot, and they would also use that to extract the specimen, and then they'd have just plus 1 more laparoscopic work.
How do you inflate this space inside?
Pardon me, say that again?
How do you inflate the space inside?
How inflate?
How do you inflate it?
Oh, so there's been experiments. Rachael mentioned what's been done in the past. The only kind of surgery that's been done in space has been small animals, rats. They're used for all kinds of models, and they need to sacrifice them at different points. And so that's the kind of thing that's been done. Nothing like this. Now, on the zero-G flights, where they take the airplane and they fly and they get this, there's been animal experiments for that, and they do insufflation differently, actually. Rather than, they'll have inflatable structures inside the body that will support the abdominal wall and control the organ location. So there's kind of a different approach to that. All that's definitely in the research area, and again, it'll be a while before we do surgery in space. Yep.
The insertion of that, does it go through a sheath, like current endoscopic?
Yeah, so this actually passes, again, with the FDA approval, it passes through what's called a hand assist laparoscopic port, which is just a big blob of silicone that you kind of, it's made so surgeons can stick their hand inside there and kind of help themselves with laparoscopic surgery. That's commonly used in colorectal procedures, again, because you need a hole to bring the specimen out, and we use that for this device. We're currently developing our own port that will simplify that, but yeah. Yes?
So I'm assuming eventually a continuum of the surgeon providing, say, an appendectomy remotely or laterally, but then an advanced equipment would be that some sort of AI or automatic pre-program, for example, do an appendectomy. That would be the ultimate.
Yeah,
Is there anything along the continuum?
yes, there's lots of, and that's the right word that I was using, there is continuum. So right now, every motion of this, actually, I would go back a little bit. Laparoscopically, everything that's done is done by the surgeon, right? Every little motion. We'll stop the surgeon if they're doing something wrong, right? So we intervene a little bit, but not much. It's mostly just the motion of the robot. Now, on the other side is what you said before. Actually, let me go even further out. My idea was always for a darker problem would be, here's a big blue pill and here's a big red pill. You take the blue pill first, and the red pill, that's going to make you sleep. The red pill is actually a robot. It's going to go in, and when you wake up in 14 hours, your gallbladder will be gone. That's the way out there. So somewhere in between those two things. Now, where we will go next, I believe, is more like a horse. So again, picture driving a remote control car around the room. You're again controlling everything that it does. But that's not true when you're on a horse. You kind of give it high-level commands. You kick the horse, we're going over there, go through this gate, but you're not telling it where to put its feet. You're not telling it how to balance. You're not giving it every little detail, that it's figuring out a lot of stuff on its own, but it's taking high-level commands from you. So we've actually used some neural networks to do some things like, just the next simple thing is just touch that piece of tissue, and it will reach out and touch that piece of tissue. And so we've used artificial intelligence neural networks for those sorts of things. Then it's going to be grab that and cut along this line. And there'll be higher level commands that are issued, and we'll slide along that continuum until we get to more autonomous surgery. Surgeons' jobs are very safe, but it'll take a long time. And there's a lot of expertise in there. It's a lot more than, Facebook is very proud about how they can find every picture of me in the world, right? It's much harder to do even a gallbladder removal with some unusual anatomy than it is facial recognition and some of these. So it's a hard problem, it really is. We're building a new console, actually, that's just jam-packed with GPUs. I don't know if you guys are any gamers in the room or AI people in the room. They know graphical processing units are kind of machines that make AI possible. So we're going that direction, for sure. Thank you very much.
I'm happy to present our last speaker, Dr. Francesco Bianco. Dr. Francesco Bianco is an associate professor of surgery with tenure at the University of Illinois at Chicago. He serves as a staff physician at UI Health Medical Center and Mount Sinai Hospital, Chicago. He holds a position as faculty in the general surgery residency program at both the University of Illinois at Chicago and Mount Sinai Hospital. In addition, he is the director of the general surgery clerkships at UIC and has won multiple teaching awards from the medical students, including 3 Golden Scalpel Awards and 1 Polito Award for his excellence in teaching. As one of the early adopters of robotic surgery, Dr. Bianco has been actively involved in this field since 2003. He is a faculty member of the International School of Robotic Surgery in Grosseto, Italy, as well as this SITL lab at the University of Illinois, Chicago. Dr. Bianco's experience in advanced robotic surgery techniques has led him to train and proctor over 260 surgeons from around the world. Dr. Bianco holds a position as one of the founders and executive members of the Worldwide Clinical Robotic Surgery Association and has an active presence in various national and international surgical societies. His primary focus lies in the development of innovative surgical peer-reviewed publications. He lies in the development of innovative surgical technologies and the clinical application of new robotic platforms. He has published over 150 peer-reviewed publications and 15 book chapters related to minimally invasive and robotic-assisted surgery. Recognized as a leading authority in his field, he has been invited to deliver lectures and perform live surgeries at prestigious national and international meetings. Please help me to welcome Dr. Bianco.
Thank you for having me, and for me it's a pleasure Sorry for the long introduction, I should send a shorter version. But it's really a pleasure to be here in Chicago, what I call home. I'm Italian, I moved here in 2007, so I feel like it's my home now. And share with you this exciting experience and what we have done. And I was lucky enough to share this experience with Shane, with Rachael, and all the team and with Incision. I decided to give you a little bit more context about robotic surgery and give you a little bit more information about what it is and what we are doing in a wider picture. And of course, when we talk about robotic surgery, we need to start, and now we are in the museum here, we have a lot of history, and we need to start from the French Revolution. The French Revolution was, in surgery, the introduction of laparoscopy. So, for the first time, we were able to perform surgeries through very tiny incisions, avoiding big cuts and preserving the integrity of the abdominal wall and being less traumatic. This was a true revolution because if you think about it, in 1987, the first cholecystectomy was described, and without any scientific support, any strong evidence, by 1993, 80% of the cholecystectomies were already done laparoscopically. We have never seen in surgery something like this again, because there was such a huge adoption without very much scientific support. So this is the beginning of this new technology, but we start to understand also more about the limits of this technology, right? So everything we do when we do these surgeries is reversed. If I want to move my instrument down, my hand needs to go up. If I want to go right, my hand needs to go left. So this takes time to learn this technique, and of course, it compromises a little bit your precision, and your fatigue over time becomes exponentially bigger. We work in laparoscopy using three-dimensional screens, so we lose the depth of the perception of the depth of the field, because now we look at 2D images. It's sometimes in a very uncomfortable position. You're working in one direction and looking in another direction. So together with the limits again, we saw the opportunity, and this is the really big merit of laparoscopy at this point, was the merit to transform something very complex like the human hand into something much more simple, like a laparoscopic instrument that has only very limited movements. It opens and closes, it goes in and out, it can rotate. So we simplify in something that is extremely, extremely challenging and complex like the human hand. And this, of course, now is the basis to build robotics, right? So, as Shane was mentioning, in the 90s, there was a lot of excitement about telemanipulation, remote surgery. There was the Cold War, the atomic bomb, everyone was concerned about giving health support for surgery in contaminated battlefields, or those were years where we were talking more and more about the space stations, the exploration into space, and this concept of remote surgery became more and more popular. So you can see here, we start to do the first work in terms of telemanipulation. Some of these projects lost momentum, and a lot of these patents were sold by NASA and the US Army to private companies. The first one was computer motion. They came up with the Zeus surgical system in 1998, and this is really the first more commercially available system, which is the intuitive surgical, introduced first in 1999. This is a picture of Guibert Cadier. He's one of the very first surgeons to perform robotic surgeries. This was in Belgium. And as Shane likes to show rockets, I always like to show this picture of a younger me with a lot of hair. So this was a picture of me next to Guibert at the times of the very beginning of this history of robotic surgery. My time started in 21 years ago. I was living in Tuscany. I went to see this crazy surgeon who was doing a pancreas resection with the robot, liver resection, and then we started working together, and I've been working together with him since then. Louder? Okay. We've been working together since then, and he's actually here. He's still the chief of surgery here at the University of Illinois in Chicago. a true pioneer in this field. And I was lucky enough to follow him with his experience. We started with the very first model, and then we saw the entire evolution of robotic surgery with all the different technologies. Currently, robotic surgery is a gold standard for many applications. We use it in many different fields. This is a very short list, but we use it in general surgery, gynecology, neurology. We are developing more extreme applications, like in transplant, for instance. And we learned about the system and technology and what are the advantages of this technology. We know that there are some surgeries nowadays that can only be performed with a minimally invasive access using a robot. And this is the example of kidney transplant, which we developed here for the first time worldwide at the University of Illinois. Liver transplant, complex hernias, cellular cancer surgeries can only be performed minimally invasively using a robot, not laparoscopically. Other surgeries are improved by the use of the robot, like hiatal hernias, removal scar tissue, and other different applications. And you know what are the advantages of the system. Here are some examples. You can see that the pointer is not working. Oh, yeah, it's working. Here we have the ability with the robot to downscale our movements. So if we move our hand 5 inches, the robot will cut it down to 1 inch, for instance. And this allows us to be extremely precise. The robot can cut all the algorithm, with an algorithm can cut all the tremors of the hand. So every movement that is above a certain threshold gets eliminated, and the instruments are extremely steady and precise. This enables us to do micro dissection, work on very small anatomical details, and be extremely precise. We have a very high quality vision that we can rely on while sitting comfortably at a console. We don't have to struggle with the vision. We have the possibility to reproduce more precisely the movement of the hands inside the abdominal cavity. And we are at a stage where, like this is a self-portrait of Magritte, called the magician. He's doing multiple things at the same time, right? We can move our camera, we can control our instruments, we can do more complex and sophisticated things than before. We are much facilitated in suturing through these small incisions. We can bring more information inside our surgical field during surgery. We work much more comfortably. And comfort for a surgeon means also working longer. It means working on more complex things, maintaining that same level of precision that you have at the beginning of the case. And it also means working more years. So you can retire later because you don't have all the limitations, shoulder injuries that is typical of laparoscopic surgery. And then we have the possibility to simulate and use the computer to take advantage for training and exercise before doing some surgeries. Here is an example of an interesting thing that they discovered thanks to a robot. If you take a 1 penny coin, I don't know if you ever took the time to look carefully, but I was using it to show the magnification of these robotic platforms, and I discovered that inside there is a little statue of Lincoln inside the memorial. So I don't know if you ever noticed, but this is something I noticed for the first time thanks to the robot. And the level of magnification of these images and the details that you can get from this. So, of course, what are the advantages of all this technology for our patients? We can be much more less traumatic and cosmetic. This is not real, but this is an example of what would be a cut for a liver resection. And now we can do the same thing with liver cuts and a tiny incision to remove the specimen, like Shane was mentioning for the colon, from a different side, right? We are able, because of the faster recovery of these patients, to start the oncological treatments sooner, so they don't have to wait a certain amount of time before starting chemotherapy, for instance, because the recovery is faster. We are forced to use, to be much more clean during our surgeries, and this means that we reduce as much as possible the blood losses, because blood takes light, and light is vision for us during this surgery. So we are much more precise during the dissection. And as we mentioned, there has been an evolution of this technology, and you can see all the different versions of these robots. And this is the latest one. This is not even FDA approved in the United States. We had 3 of these robots at the University of Illinois, and done more than 450 cases already with this technology. So I'm very familiar for this new platform, which uses a single port like the Mira. This is one of these systems in our lab and in Chicago, and you can see that it's huge. This is the first thing that you really notice, is a huge system. The instruments can move, there is a video there, can we start this? Thank you. We can do small incisions that can barely be noticeable. This is a gastric resection, for instance. This is a cholecystectomy. And you can see these are very, very gentle surgeries with incisions that almost disappear, right? We're not increasing complexity with these surgeries because, as you can see, those are the reports from the timings. We do cholecystectomies in 6 minutes, inguinal in 18 minutes. So we are extremely efficient with these surgeries while being extremely conservative on the abdominal wall. But there are limits. This technology is not perfect. This technology is extremely expensive. Think about it. One system costs up to 2.5 million. So it's not a technology that can be available everywhere, that everyone can use or that everyone can take advantage to it. These carts are huge. Those are like, as Shane was mentioning, 2,000 pounds. We call it the friendly way, the 900-pound gorilla in the room. That's how we call our robots, because these are robots that take sometimes some engineering work to be to prepare the rooms to host these very heavy carts, right? So it's a very, very logistical, it's a very, very labor-intensive type of thing. These rooms have dedicated robots that are stored in these rooms, and they cannot really be moved around because those are so big that this is a problem. And this brings to the next limit, that is limited access. If you have one robot, $2.5 million, sitting in one room, you will be able only to do a certain number of cases, with many other surgeons waiting in line to use the robot when it's going to be their day, or things like that. So either you invest millions, like at the University of Illinois, we have 7 of these robots, so, but it's a huge investment, right? Not everyone can do that. And so that will be a limit in the access to this technology. And then, of course, the need of having specific training for these technologies. You have to be trained in using this specific tool. And once you start using it, you're pretty much on your own. You need to be proficient and completely autonomous in these technologies. The big difference, and the reason why these things are so bulky, so heavy, resides in a very tiny little detail, and it's this one. All these robotic instruments, the traditional robotic instruments, rely on little cables to operate. So we have a huge machine that moves tiny instruments through some cables. This is a little bit, we can start this video like a marionette. So we have someone with...
Oh, we have a detachable leg arm?
Stop here.
So he can do...
No, it's okay. You can go back, and you can click, and then in the corner there will be the audio. You will need someone that is there to control this tiny instrument. So you cannot really miniaturize anything beyond a certain limit, because there will always be need for some sort of external control. And as you can see, the marionette can do a lot of sophisticated movements, but there is still a limit in this design. What is the revolution and the merit to the genius of Shane at recognizing this is changing the game. Let's do things differently. Let's think in a different way. This technology has some limits. Let's try to overcome them. Now you can see the Mira next to a standard robotic platform, and you can see where is the genius. The genius is miniaturization thanks to a completely different design. Now we don't have the 900 power gorilla anymore. We have a tiny robotic system next to our patient, right? This is a comparison of the sizes to give you a better understanding of the difference in the platforms. And that's all you need in your operating room. You are not taking space, you are using the space for other things, more important things. Like, and this is the genius. The genius is in the introduction of motors that control the arms. These motors are not reliable cables. The motors actually move in different segments of the arms. And they are strong, as Shane showed you. They can do lift-ups, they can lift weights. They are extremely strong, and they are extremely efficient. And they can eventually be much more autonomous than a marionette. They can do much more sophisticated things because they don't need someone to control them from the outside in terms of the mechanics, right? So those are completely independent. This is the marionette from before, just to show you. The other advantage is in the future developments. This is a technology that now is like this, but in the future it will become smaller and smaller as the technology progresses. And this design will enable this technology to become smaller, right? It will be miniaturized as much as possible in different generations. There are things that I know that I don't know if I can share, so I will not, but maybe Shane can mention something later. This technology is need to be becoming smaller and smaller. And when we become smaller, now we can think in a more creative way, using this technology to access our surgical regions in a different way. We can access our surgical targets through the mouth, through all the natural orifices, and we can go and work on the colon, maybe through the mouth. We can do a cholecystectomy, entering in the stomach and going out into the abdominal cavity. So there are many more things that can be done. Another important aspect, and this is the value of also of this space exploration, is the ability to bring our surgical skills to more people. We cannot invest in this remote island on a $2.5 million robot that can maybe be used by one surgeon, maybe, I don't know, on 2 patients, right? But we can definitely bring a mirror there and then the possibility to connect remote and offer advanced robotic technologies to every patient. Another example, another remote village in the middle of nowhere, you can arrive with your mirror box and be able to perform surgeries also in these remote locations. And this is, of course, the situation with elective surgery. So you can plan these surgeries and be able to perform these surgeries from a distance in selected spaces. But then there is another even more exciting to me aspect, which is the emergency box. I call it, you leave a mirror on the wall in your operating room, and if the surgeon is in troubles, you break the box. I'm joking, of course, it's not sterile, but you bring the system, you bring the system by the surgical field, and now you connect with the surgeon from Chicago, from New York, from another location that can help you finish the surgery and save that life and reduce trauma and sufferance to the patient. So there is even another layer of utilization of this technology when it's so miniaturized. Then, of course, we will have a mix of emergency surgeries, elective surgeries, and then, of course, the inevitable evolution will be also the ability to perform surgery in space. Of course, I have to put some pictures about this because I'm very excited about this experience. I was very lucky to be invited to be sharing this experience with virtual Incision and work in the space station. The space station is a crazy place. I don't know if you read or heard about it, but it's an unbelievable place. It's a 6-bedroom house with a volume, pressurized volume of pretty much the same volume of an Air Force Ones at Boeing 787. And it floats around the Earth at 250 miles. And it is a rocket that was at 500 miles an hour. It's like one of the fastest objects ever made by man. So it rotates every 90 minutes, it completes a full rotation about the planet. So during the day, you see 16 sunsets and 16 sunrises. When I was there for the experiment, we saw few sunsets and few beautiful sunrises during the experiment because the space station keep going around at an incredible speed. And if you want to click on this video, this is a video I found on YouTube, you can see if the system was flying at 10,000 feet, this is what you would see. You would see something very visible moving at an incredible speed, right? So now imagine us sitting comfortably at this console, controlling with very good precision still, something that moves so fast. To me, it's mind-blowing. It's like incredible, right? It's one of the most extreme places in the world. And here you can see again the control center with the feedback from oh, this might be the video, sorry. The feedback from the space station and from the NASA offices. And this is the evolution, and this is where it makes me even more excited, because this is what we're working next. Next is going to be bringing these robotic abilities to our patients on the planet. So this was something we did in April 30th. We connected from Chicago to Lincoln, Nebraska, and a group of 4 surgeons in each place were able to perform the surgery on an animal model. And here you can see we are working here, and again we have a direct vision and connection from Nebraska. Now this is a major thing because we only had 15 milliseconds delay. In surgery, and in robotic surgery, anything that has less than 200 milliseconds is not even noticeable by the human eye. So we cannot tell there is a delay if it is less than 200, 150 milliseconds. So 15 milliseconds is an incredible number. It's an incredible technology. So this is made possible by a collaboration between Virtual Incision and another company that builds these networks and secures them and make them safe to connect with a sophisticated interaction. Those are where the 4 surgeons in Chicago and in Lincoln. Next will be, I don't know, we are thinking about the name, but probably it might be the Route 66 surgery, Chicago to Los Angeles. We connect from University of Illinois to City of Hope and perform surgeries. We expect the latency to be about 18 milliseconds because that's what the standard is at that distance. So we will see. We'll keep you posted on this. But again, those are the possibilities that really excites me and can make a difference for our patients here on Earth. And all this while being comfortably seated at the console without having to worry about your shoulder, about your vision. You are like very comfortable. I like to show this picture. This is my motorcycle. This is not me, but a Moto Guzzi, Italian motorcycle. You can drive this motorcycle for hours. I do, and I love it, and I'm very happy, and I'm very comfortable all the time. And if you think about it, the position that you have when you do laparoscopic surgery is completely the opposite, right? You have your hands up here in a very uncomfortable position. Look at this surgeon holding his hand for a long time in this position. Vision, you look in one direction and you move in the opposite. So again, extremely comfortable. And then what is the future? Because this is the present, and that's exciting. The future of these systems will be smaller, and with time we will see even Rinard getting smaller and smaller and use new access for surgery. All the natural orifices can become an access for a surgical procedure. They will be more affordable, and Rinard is leading this transformation in many different ways. The design of the system, the use of new materials, the technological advancements will make this even more economic, and many other features that are changing things. And then, and this is the last segment, these robots will become smarter, of course. We have improved so far our hands and our eyes. We can see better, we can move in a more precise way. But the true revolution of robotic surgery is in something else, even more sophisticated. And this is the way we change the interaction with our patients. Surgeons and these rooms can tell you, you will find all the history about it in these rooms. Has always been a direct interaction between the surgeon and the patient. The surgeon relies on his own eyes, on his own hand, strength, vision, knowledge to operate on a patient that is right in front of him. Robotic surgery changed this interaction because now in between our patients and the surgeon there is a computer. So we open this world to digital surgery and to all the possible interactions that can be connected to the digital world. Right? So we can have, again, the ability to simulate our surgeries. We can train the day before using the CT scan or the X-rays images of an actual patient. We can reconstruct the anatomy and train on that surgery the day before doing the actual surgery. This is an example of the University of Illinois, our residents train. They can use some sort of video games that simulate the actual anatomy to perform surgeries, to learn how to do surgeries without exposing anybody to the risk of learning curves or using expensive alternative models. So they become proficient at their own pace. They can come to our lab, and whenever they are done, at the end of the day, they can sit in the console and do surgeries all the rest of the hours they want. So much, much efficient and safer. We will have the possibility to implement information in real time. So this information will guide us to our surgeries and will tell us, you can cut here, you can reset here, this is where the tumor is. And these are very advanced things that are already happening right now. And then, of course, the remote presence with the new technologies like 5G. 5G is already able, by bandwidth and speed, to support remote surgery. So technically it will be feasible. It's not safe enough yet because there are a lot of things that can disrupt the type of communication. But these are things that we can get better. So even now we can think about maybe place one of the MIRA military station or a boat, military ship, and have it there for our marines. And then the ability for the computer to remember millions of patients, millions of surgical procedures, millions of books, combined with the ability to recognize anatomy and anatomical structure to guide you and tell you, look, you are in this situation, if you want, you can use the Giulianotti's solution that he used in 1999, right? It's like playing chess against the computer. The computer, this with me, always wins, because he knows all the moves. So the computer can really guide you and take you out of difficult situations. Artificial intelligence is able to recognize already now, through this is virtual colonoscopy, you can recognize cancerous polyps just by the way they look. So the computer can tell this is cancer, this is not, and guide you there. So maybe if you are having a bad day, you might miss a little cancer, computer will not. Or the computer will be able to analyze our performance and say, Dr. Bianco, you are not a safe surgeon, you should go back to training. You know? And these are things that are important because, again, it's all for our patients. And then, of course, the last level will be automation. We will be able to teach the computers how to do some steps, and they will be efficiently replicated. This is one of the projects we have at the University of Illinois. We are teaching a computer how to do polysystectomy together with the Fermi lab that you probably know about. So this will be probably the next level, and there are a lot of legal implications connected to this. Again, this is where we are going with the idea to make everything efficient and safe. We have different timelines for some of these applications, but most of this revolution will happen in a very short period of time. We expect the next 5 to 10 years to be already bringing a huge amount of changes in surgery. We will not be able to recognize surgery the way it's done now. And this concludes my presentation. Here I have my email, so feel free to reach out if you also have any questions, or you want to come to see the lab. And I usually have this sentence that says patient first always, and not for this presentation. Thanks to Mira, you can say no matter where they are. So thank you. I don't know if there are any questions. Yes.
I have a question about, when you talk about 5 to 10 years, and you look at the United States of America and our healthcare payment system, how would you anticipate an even access to this kind of technology when our insurance system with multi-payers is so out of control?
Yeah, that's a great point, a great question. I think that is why making this technology more affordable is a problem. We need to be responsible. We cannot bring new expensive tools without considering the impact on the healthcare system. We need to start to be considerate now. And that's what I appreciate about the company. Attention also to this aspect, right? Because this is the next level. We need to be wonderful but affordable, because we cannot continue at this pace. It's not sustainable. So we need to change this.
In regular robotic cases or laparoscopic, you can switch the handles because they're small. With this one, how do you, if it's only one hole, how do you switch it from procedures to?
When you need to switch instruments here, you can easily move this in and out. So you can remove the system, change the instrument, which, and in this case, the instrument is like a little T, like you can probably see. And that's all.
So you take the whole thing out.
Yeah. Yeah, and you bring it in again.
So the plan is just to only have one incision, or you're gonna have four?
You can normally you use two, right? Because you will have one incision that is the side where you will remove your specimen, and that's where the system goes. And then you have a little extra incision that allows you to put the camera, the action. You can have an extra assistant on the back side. And that could be a 5 millimeter or 10 millimeters, so very, very small incisions. That's perfect.
I'll ask one other question. Always when technology is galloping ahead, we learn about things that we can do, and then later think about what we should do or what we ought to be doing. And I'm curious about any sort of bioethical input into the development of these sorts of life-changing.
You know, this is a good point. There is a saying, I know it in Italian, I try to translate it in American, I'm sure it's also American, that when you explore the limits, you make the navigation safer also within those limits, right? So our role here, I think we all are pointing at that. We are trying to push the limits. We are trying to explore new things. We are trying to expand new things. And of course, the bioethical aspects are very important. But we are in a privileged position somehow, because we are building new things, of course, respecting safety of our patients and everything. And then this becomes standard at some point, right? When all this routine is accepted, approved, validated, then we become standard, and then you will see a lot of these things within the limits, in the safe navigation area, when everything will be safe. That's why to introduce this system for clinical use, there are 35,000 pages of paperwork to make it happen, right? So we push the limits in the space, but then to be able to navigate within the limits, we need 35,000 pages.
Thank you so much. Thank you all so much for coming. Please view the exhibition on the 4th floor. This evening, we will have an additional reception at 6 p.m. featuring Dr. Megan Everett from NASA and the International Space Station. So I hope you can join us then. But thank you all so much for coming.
Michelle, is it true that there's a live demo of this evening as well?
Live demo, unfortunately, they couldn't have